Welcome to ArcTech AI Institute. Today, we unravel the probabilistic foundations of generative AI, a crucial bedrock for true understanding. Variance, sigma squared, or its square root, standard deviation, sigma, determines the spread or width of the curve. In variational autoencoders, or VAEs, the latent space is often assumed to be a Gaussian distribution. Diffusion models gradually add or remove Gaussian noise to transform data into noise, and vice versa. The Bernoulli distribution models a single binary outcome, success or failure, yes or no. Think coin flip. Its probability mass function, or PMF, gives the probability of each discrete outcome. The single parameter p represents the probability of success. 1 minus p is the probability of failure. Bernoulli is ideal for modeling binary data, like pixels in a black and white image, or activation states. For multi-class, discrete data, we extend to the categorical or multinomial distribution, common for text generation. Now, let's explore Bayes' theorem, a cornerstone for understanding how to update beliefs with new evidence. Bayes' theorem builds on conditional probability, PA, given that B has occurred. Generative AI models learn the underlying probability distribution of training data to create novel, similar examples. Here is Bayes' theorem, stating the posterior probability in terms of prior, likelihood, and evidence. P is the posterior probability, the probability of the hypothesis given the observed data. The H is the likelihood, the probability of observing the data given the hypothesis is true. P is the prior probability, our initial belief in the hypothesis before seeing any new data. D is the evidence or marginal likelihood, the overall probability of observing the data acting as a normalizing factor. Bayes' theorem elegantly quantifies how we update our confidence in a hypothesis after observing new data. Inference in VAEs, finding the latent z, given observed data x, is fundamentally a Bayesian problem. P of z given x. Diffusion models implicitly leverage Bayes' theorem in their reverse denoising process, estimating P of xt minus 1 by xt. Ultimately, generative models aim to learn P of data, or the likelihood of observing the training data. A strong grasp of probability and statistics is indispensable for diagnosing, improving, and innovating generative models. The very act of generation is about sampling from this learned probability distribution, creating data that appears authentic. Thank you for joining this foundational journey. In our next tutorial, we'll delve into specific generative model architectures. Likelihood quantifies how probable observed data is under a given model or distribution. It's not a probability of the model. Generative models are often trained by maximizing the likelihood of the training data under the model's parameters. To model data, we use probability distributions. These mathematical functions describe the probabilities of different outcomes. The Gaussian, or normal distribution, is ubiquitous. It's characterized by its symmetric, bell-shaped curve. Its probability density function, or PDF, gives the relative likelihood of a random variable taking a given value. The mean, mu, dictates the center or peak of the distribution, representing the average value of the data.